Hello everyone, I'm Zhaozhuo from RISE. Today I'm going to introducing a paper, Locality Sensitive Teaching. This is a joint work with Beidi, Chaojian, Weiyang, Professor Le, Professor Yingyan, and Professor Anshumali. In this paper, we talk about the task called machine teaching, an inverse problem for machine learning. In the machine teaching paradigm, a machine teacher has a model for a task. Then the machine teacher wants to teach the student this model. However, the student cannot have access to the teacher's models. For example, the student is either a human or the student uses a different model for the same task. Therefore, the machine teacher should feed examples to the student with the knowledge learned from the W star. Machine teaching has a wide application in personalized education. During this COVID pandemic, in-person education would be infeasible. Machine teacher helped to rectify this issue by providing more interactive and personalized education at home. Students can use mobile apps such as Duolingo to enjoy the service provided by machine teachers. Among the current machine teaching paradigms, iterative machine teaching provides the most frequent teacher-student interactions. In IMT, we formulate the cognitive model of the student by a parameter W. Given this current W, IMT performs a greedy search through the teaching materials following the formula as below, and then selects the most suitable teaching example. Then IMT feeds the example to the student for learning. One significant problem of IMT is that the teacher needs to traverse all the samples in the dataset. This expensive greedy search limits the practice usage of IMT. The intuition of IMT is also against our common sense. In education, an inexperienced teacher would go over all the available books and papers to find the suitable material for the next class. However, an experienced teacher would quickly locate the chapters in the book and prepare the most suitable materials for the next class. We mimic this intuition and provide locality sensitive teaching, namely LST. LST avoids the traverse over all the examples. Instead, LST uses a hash table to categorize the teaching examples. When we get the student's information, LST direct performs lookup in the hash table and traverse the suitable example. Therefore, we significantly reduce the time cost of greedy style traverse. To do this, LST reformulated the original optimization problem in IMT as an adaptive inner product sampling problem. We rewrite the greedy teaching algorithm as a maximum inner product search algorithm. And then we could use efficient locality sensing-based data structures to sample the teaching examples through the hash table. Here we introduce more details about hashing-based sampling. In the pre-processing step, we map the teaching example xy to a vector called fxy. We are using a transform called f. Then, given the current student's cognitive model and the optimal model W star, we use a transform G to generate a vector in the same direction with fxy called GWW star. Finally, we use this GWW star as a query and look up the suitable materials from the hash table. This hash-based sampling is first proposed by Spring and Shrivastava in 2017 and achieved promising results in kernel density estimation and other machine learning tasks. To further illustrate how we do LST, we perform a toy example by letting the machine teacher teach a machine learner to understand what is the COVID city images. We find that using the LST, the examples extracted by the hash tables are more diverse and more confusing images of the COVID city images. However, the IMT greedy style algorithm keeps selecting 2 images during almost 10 iterations. Finally, we introduce our experiment. We choose our task as a regression and classification. The teacher model is trained on teaching examples. Given the student cognitive model with random initialization, the teacher requires to feed the student 1 example per iteration. We use the speed towards convergence as our evaluation metric. As shown from the result, LST outperformed IMT with a huge savings in the running time. Meanwhile, LST achieved the same iteration-wise convergence with IMT. We also firstly deployed the LST on an NVIDIA TX2 edge device, and then we measured the energy consumption of LST and IMT. We observed that LST achieves up to 99% 76 saving of energies over IMT. In this way, we show that LST enables efficient machine teaching on IoT devices. To sum up, we propose an efficient machine teaching algorithm using advances in efficient statistical sampling, which enables real-time feedbacks between the teacher and the student. Moreover, we introduce a huge number in the energy savings and enable machine teaching on practical usage on the edge devices. Thanks for listening. Hope everyone enjoyed the conference.